Hi everyone. In this session we will see applications of differential equations of first order. So first is orthogonal trajectories. Right? Two families of curve such that every member of either family every member of either family cuts each member of the other family at right angles are called orthogonal trajectories of each other. Right? Now procedure to find orthogonal trajectories. Step 1. Form its differential equations. Form the differential equation of given family. Step 2 is replace dy by dx by minus of dx by dy so that the product of their slopes at each point of intersection is -1, and replace 1 by r dr by d theta by minus r d theta by dr for polar form. To get orthogonal differential equation. Step 3 is solve the differential equations. Solve the differential equations of the orthogonal trajectory. Okay. Let us see one example. Find the orthogonal trajectory. Find orthogonal trajectory of family of curves xy is equal to constant. So we have given xy is equal to c. Now differentiate with respect to x. So x dy by dx plus y dx by dx, y times, is equal to 0. Now replace dy by dx by minus dx by dy. So x dx by dy is equal to plus y is equal to 0. Then we can say x dx by dy is equal to y. Now, so this is in the variable separable form. So we can separate integral x dx is equal to integral y dy. This is x square by 2 plus is equal to y square by 2 plus some constant c dash. So say the constant is k, and then x square minus y square is equal to 2k. That is some another constant k dash. So this is the orthogonal trajectory of given family of curves. Okay. Now let us see the orthogonal trajectory of polar curve. Okay. So find the orthogonal trajectory of r is equal to a times 1 minus cos theta. Okay. Then differentiating r is equal to a times 1 minus cos theta. So if we differentiate d with respect to theta, so dr by d theta is equal to a minus a cos theta, which is minus of minus a sin theta, that is a sin theta. Now one by r dr by d theta is equal to a sin theta by a times 1 minus cos theta. Then we have replace 1 by r dr by d theta by minus r d theta by dr. So replace by minus r d theta by dr, which is equal to 2 sin theta by 2 cos theta by 2 divided by 2 sin square theta by 2. Sin theta by 2 get cancelled. So we are left with cot theta by 2. D theta by dr. Now we obtain tan theta by 2 d theta and plus dr by r is equal to 0. Now this can be rewritten as dr by r minus of sin theta by 2 by cos theta by 2 d theta. So this is the differential equation of orthogonal trajectories. Then there are physical applications such as motion of a boat across a stream, resisted motion, or atmospheric pressure, etc. Then we use differential equations in electrical circuits. Okay. Next is Newton's law of cooling. Okay. So according to this law, the temperature of a body changes at a rate which is proportional to the difference in the temperature between that of the surrounding medium and that of the body itself. That is d theta by dt is equal to minus of k theta minus theta naught, where k is a constant and theta naught is the temperature of the surrounding, and theta is the body temperature at any time t, right? Now, by variable separable, using variable separable, we can write this as d theta by theta minus theta naught integral is equal to integral minus k times dt, which will be equal to log of theta minus theta naught is equal to minus kt plus some constant. Now we can replace this constant by some another constant, log of c. Now taking log of c on the left hand side, we have theta minus theta naught by c is equal to minus of k times t. Again taking anti-log on both sides, we have theta minus theta naught by c is equal to e raised to the power minus kt. Now we can take this c on the right hand side. So this is the required solution of Newton's law of cooling. Next is rate of decay of radioactive materials. So this law states that disintegration at any instant is proportional to the amount of material present at any time t. Then du by dt is equal to minus ku. So where k is a constant, right? And u is the mass of material at any time t. Okay. So again, by using a variable separable method, we have du by u is equal to minus k times dt, and now integrating both sides, we will have log of u is equal to minus k times t plus again some constant log of c, so which will be equal to u is equal to c e raised to the power minus kt. So this is the solution of law of decay, right? Again, we have law of growth. The rate of change of amount of a substance with respect to time is directly proportional to the amount of substance present. Say du by dt is proportional to u. Okay. Say k will equal to k times u. So here notice that Here I have taken negative sign because it was decay here, and here it is going to be a growth, exponential growth. So that is why I have considered positive sign here. So again, taking variable separable, du by u is equal to integral k times dt. So which will be equal to log of u is equal to k times t plus log of c, then u will be equal to c times e raised to the power k times t. So this is the solution of law of growth. So next is linear differential equations. Linear differential equations. So linear differential equations are those in which the dependent variable and its derivative occur only in the first degree and are not multiplied together. Thus the general linear differential equation of nth order is of the form d power n y by dx n plus p1 d n minus 1 y by dx n minus 1 plus p2 d n minus 2 y by dx n minus 2 and so on. Plus k times p n y is equal to x, where p1, p2 r and x are functions of x only, right? Linear differential equations with constant coefficients are of the form so I replaced p1, p2 and pn by k1, k2 up to kn, right? So where k1, k2 and up to kn are constants and x is a function of x only, right? Now to solve such equation, such differential equation, we have the complete solution as y is equal to complementary function plus particular integral. Okay. So in order to solve this question relating linear differential equations of nth order and first degree, so we have to first find complementary function, okay, and then the particular integral, particular solution. So let us denote d by dx as d square by dx square as d square, d cube by dx cube is as d cube, etc. Okay, so that dy by dx is equal to d times y, d square y by dx square is equal to d square y, and so on. right? Now rules for finding complementary function. Okay. So we can write the equation, this equation as d raised to the power n plus k1 d raised to the power n minus 1 plus k2 d raised to the power n minus 2 up to kn to y is equal to 0, right? Where k1, k2, k3 and kn are the constant. Now so this can be rewritten as, if all the roots are real and different, case 1, if all the roots be real and different, then this equation is equivalent to d minus m1, d minus m2, d minus mn, y is equal to 0, right? Then this will be satisfied by the solution of d minus mn y is equal to 0, that is dy by dx minus mn y is equal to 0. This is a Leibniz linear form and integrating factor is e raised to the power minus mnx. Thus the complete solution will be y is equal to c1 e raised to the power m1x. Okay, so see, this, if integrating factor is e raised to the power minus mnx, then that means its solution is y e raised to the power raised to the power e minus m n x is equal to cn, or y is equal to cn times e raised to the power mnx. Similarly, other factors can be taken in any order, and it will be satisfied by the solution of d minus m1y is equal to 0. Similarly, d minus m2y is equal to 0, etc. And y will be equal to c1 e raised to the power m1x, y is equal to c2 e raised to the power m2x, and etc. So the complete solution will be given by y is equal to c1 e raised to the power m1x plus c2 e raised to the power m2x plus cn e raised to the power mnx, right? So this is the complete solution. Next, case 2. If the two roots are equal, that is m1 is equal to m2, then the solution becomes c1 plus c2 e raised to the power m1x plus c3 e raised to the power m3x and so on. Okay, and we can replace this c1 plus c2 by one arbitrary constant c, right? Since it has only n minus 1 arbitrary constants and therefore it is not the complete solution. So in this case we proceed as the part of the complete solution corresponding to the repeated root is the complete solution of d minus m1 y is equal to 0. So putting d minus m1 as z, d minus m1 y as z, then d minus m1 z is equal to 0, or dz by dx become dz by dx minus m1 z is equal to 0. So this is again a Leibniz linear in z. Then integrating factor is e raised to the power minus m1x. Now its solution is z e raised to the power minus m1x is equal to c1, or z is equal to c1 e raised to the power m1x, right? So now t minus m1 y is equal to c1 e raised to the power m1x, or t minus m1 y dy by dx is minus m1y is equal to c1 e raised to the power m1x. Again its integrating factor being e raised to the power minus m1x. Then the solution of 1 becomes y e raised to the power minus m1x is equal to integral c1 e raised to the power m1x dx plus c2, which is equal to c1 x plus c2, or y is equal to c1x plus c2 e raised to the power m1x. Now the complete solution of the original differential equation will be y is equal to c1x plus c2 e raised to the power m1x plus c3 e raised to the power m3x plus cn e raised to the power mnx. So if two roots are equal, then this is the complete solution. Okay. Now case 3. If one pair of roots are imaginary, if one pair of roots be imaginary, that is m1 is equal to alpha plus eta beta and m2 is equal to alpha minus I beta. Then the complete solution is y is equal to c1 e raised to the power alpha plus I beta x plus c2 e raised to the power alpha minus I beta x, c3 e raised to the power m3x and so on up to cn e raised to the power mnx. Now we can take e raised to the power alpha x as common. c1 e raised to the power I beta x plus c2 e raised to the power minus I beta x plus c3 e raised to the power m3x cn e raised to the power mnx. Again, by Euler's theorem, we know that since e raised to the power I theta is equal to cos theta plus I sin theta, so we have e raised to the power alpha x c1 cos beta x plus I sin beta x plus c2 cos beta x minus I sin beta x plus c3 e raised to the power m3x okay. Again, this can be rewritten as e raised to the power alpha x c1 cos beta x plus c2 sin beta x plus c3 e raised to the power m3x cn e raised to the power mnx, where c1 is equal to, you can write this as k1 and k2, where k1 is equal to c1 plus c2 and k2 is equal to I c1 minus c2, right? Now so you need to remember this solution, this pattern of solution. If one pair of roots is imaginary, so next is case 4. If two pair of imaginary roots be equal, two pair of imaginary roots be equal. Say m1 is equal to m2 is equal to alpha plus eta beta, and m3 is equal to m4 as alpha minus eta beta. Then the complete solution will be y is equal to e raised to the power alpha x c1x plus c2 cos beta x plus c3x plus c4 sin beta x plus cn e raised to the power mn x. Again remember this. See, we saw that f of dy is equal to x. So this equation has two types of solution. First is complementary function and particular integral. Contains two types of solution. Complementary function and particular integral. So note that if x is equal to 0, the complementary function is called the general solution. And if x is not equal to 0, then particular integral must exist. Okay. Now let us see some example. Solve d square x by dt square plus 5 dx by dt plus 6x is equal to 0, given that x of 0 is 0 and dx by dt is at t is equal to 0 is 15. Okay, so these are given for to calculate the constant, to find out the constant obtained in the complete solution. So in the symbolic form we can write this equation as d square plus 5 times d plus 6x is equal to 0. So now its auxiliary equation is d square plus 5d plus 6 is equal to 0. That is, so factorizing we have d plus 2 and d plus 3 is equal to 0. So where d will be equal to minus 2 and minus 3. So now complete solution is complementary function. So x is equal to c1 e raised to the power minus 2t plus c2 e raised to the power minus 3t. Okay. And when t is equal to 0, x is equal to 0. So x is equal to 0 and t is equal to 0, then c1 plus c2 is equal to 0. And when t is equal to 0, dx by dt is equal to 15 minus, okay. So let us differentiate this equation with respect to t. Differentiating with respect to t. So we have dx by dt minus 2 c1 e raised to the power minus 2t minus 2 c1 e raised to the power minus 2t and minus 3 c2 e raised to the power minus 3t. So at t is equal to 0, this is 15 minus 2 c1 minus 3 c2. So right, and now we can solve c1 and c2, and then we will get a final complementary function, or here in this case complementary function itself is the complete solution, general solution for this given differential equation, right? Now so we saw that if x is not equal to 0, then particular integral must exist. Now to find rules to find particular integral. So if f of d y is equal to x, then particular integral is 1 by f of d x. Okay, where this is called the inverse operator. Inverse operator. Okay, which is equal to d raised to the power n plus k1 d n minus 1 plus k2 d power n minus 2 x, where x is the function of small x. So case 1, when x is equal to e raised to the power ax, then one by f of d e raised to the power ax is equal to 1 by f of a e power ax, provided f of a is not equal to 0. If this fails, if f of a is equal to 0, so then this will fail. So now then 1 by fd e raised to the power ax is equal to x 1 by first derivative of fa and then e raised to the power ax. Again, if f dash a is equal to 0, then 1 by f of d e raised to the power ax will be equal to x square 1 by double derivative e raised to the power ax. Okay, provided f double dash a is not equal to 0 and so on. Okay, so let us understand this with an example. d square y by dx square plus 6 dy by dx plus 9y is equal to 5 e raised to the power 3x. Then auxiliary equation is d square plus 6d plus 9 y is equal to 5 e raised to the power 3x. So auxiliary equation is d square plus 6d plus 9 is equal to 0. So d is equal to minus 3 and minus 3, repetitive roots. So complementary function is c1 plus c2 times x e raised to the power minus 3x. Now particular integral is equal to 1 by f of d square plus 6d plus 9 to f5 e raised to the power 3x. Now since 5 is a constant, so e raised to the power 3x by put d as 3, so 3 square plus 6 into 3 plus 9, so which is equal to 5 e raised to the power 3x by 36. So this is the particular integral. Then the complete solution is c1 plus c2 times x e power minus 3x plus 5 e power 3x by 36. Okay. Now case 2. When x is equal to sine of ax plus b or cos ax plus b. Right? So then 1 by f of d square sine ax plus b is equal to 1 by f of minus a square sine ax plus b, provided f of minus a square is not equal to 0. Again, if this fails, that is, if f of minus a square is equal to 0, then one by f d square cos ax plus b is equal to 1 by f of minus a square first derivative of, and here okay, x times 1 by first derivative then into cos of ax plus b, provided f dash minus a square is not equal to 0, and this goes. So keep on differentiating the denominator until you get a non-zero value. Let us take one example. Find out the particular integral for this is equal to cos 2x particular integral is 1 by d square minus d minus 2 cos 2x. So since a is 2 here, so we have 1 by, so putting d square as minus of 4, so minus 4 minus d minus 2 cos 2x. So again this is equal to minus 6 minus d. So minus 6 minus d. So what we can do is multiply and divide by minus 6 plus d. Yes. Cos 2x. Next. So minus 6 plus d by, so this is in the form a plus b and a minus b. So this is a square minus b square. So a square is 36, minus 6 square is 36, and b square is d square cos 2x. Now d square is minus 4. So this is minus 6 plus d by 36 minus 4, 36 minus of minus 4, so 40 cos 2x. Right? Now we can write this as minus 6 by 40 cos 2x plus d cos 2x by 40. So d is nothing but the derivative of cos 2x. So take minus 6 minus, okay, leave it like this, minus 6 by 40 cos 2x plus, so derivative of cos 2x is minus 2 sin 2x. So minus 2 sin 2x, right, by 40. Now we can take out the common, minus 2 by 40. So 3 cos 2x plus sin 2x. So this is the particular integral of this differential equation. Right? Now case 3. When x is equal to x raised to the power m. So pi is equal to 1 by f of d x raised to the power m, where 1 by f of d is a inverse operator. We can again write inverse of f of d xm. So expand this f of d raised to the power minus m minus 1 in ascending powers of d, okay, and then operate in terms of dm and then operate on x power m turn by turn, right? I repeat, expand this f of d inverse in ascending powers of d as the d raised to the power m turn, okay, and operate on x raised to the power m, okay. Let us understand this with an example, okay. So we have d square y by dx square plus dy by dx is equal to x square plus 2x plus 4. So capital X is algebraic equation here. So we can write this as d square plus d x square plus 2x plus 4. Now particular integral is equal to 1 by d of d plus 1 x square plus 2x plus 4. Since we know the expansion of 1 plus d, so let us take the inverse of 1 plus d, x square plus 2x plus 4. So 1 by d, so 1 plus d minus 1 is, let us write it directly here, 1 minus of d plus d square minus d cube and so on. Okay, and x square plus 2x plus 4. Yes. Now, so this is equal to 1 by d, 1 times x square plus 2x plus 4. So x square plus 2x plus 4 minus d times x square plus 2x plus 4, again d square times d square x square plus 2x plus 4, right? Then let us operate this operator, x square plus 2x plus 4. So this is derivative of x square, which is 2x, and derivative of 2x is 2. This is 0. Again double derivative of, so x square is 2 and then 0. So now we need not consider higher power because it will become 0. Since the 3/3 and higher derivative of this equation, polynomial equation, are 0, we need not consider terms beyond d square. Okay. Now inverse operator, this is x square plus 2x plus 4 minus 2x minus 2 plus 2, which is 0, and this is again 0. So x square plus 4 only. We are left with x square plus 4 only. So inverse operator is nothing but integration. So integral x square plus 4 dx is equal to x cube by 3 plus 4x. So this is the required particular integral for the problem, right? Now case 4, when x is equal to e raised to the power ax times v, where v is the function of x. Okay. Now so 1 by f of d EAXV will be equal to e raised to the power ax by 1 by f of d plus a times v. Okay. So this operator will operate on this v, okay, capital V, where v is the function of fx. So let us solve one example. So if we have d square minus 5d plus 6y is equal to e raised to the power x cos 2x. Okay. So here complementary function is, So d is equal to, this can be written as d minus 2 d minus 3 is equal to 0. So d is equal to 2 and 3. Complementary function is equal to c1 e raised to the power 2x plus c2 e raised to the power 3x. Then particular integral will be equal to 1 by d square minus 5d plus 6, which will operate on e raised to the power x cos 2x. So e raised to the power x by 1 by d plus 1 square minus 5d plus 1 plus 6. Yes. So this was the function of f of d plus a. That is why a is 1 here. So d plus 1 square minus 5d plus 1 plus 6 and cos 2x. Now e raised to the power x. Now expand. So d square plus 1 plus 2 times d. This is minus 5d minus 5 plus 6. So which will be simplified to d square minus 3d plus 2 cos 2x. Again e raised to the power x. Now replace d square by minus 4, since a is 2 here, cos 2x. So replacing d square by minus 4 minus 3d plus 2 cos 2x. Again so minus 2 minus 3d per x, 1 by minus 3d and minus 2 plus 2 cos 2x, right? Now again I can multiply and divide by 3d minus 2 and then this will be minus ex 3d minus 2 by 3d plus 2 and 3d minus 2. This is equal to minus e raised to the power x 3d minus 2 by 9d square minus 4 cos 2x. Again put d square as minus 4. So minus e raised to the power x 3d minus 2 by 9 into minus 4 cos 2x. So which is equal to e raised to the power x 3d minus 2, and this is minus 36 minus 4, that is minus 40. So minus plus, so e raised to the power x by 40 cos 2x. Yes. So e x by 40. Now 3 cos 2x minus 2 times cos 2x. Okay. So this will be equal to e raised to the power x by 40, and derivative of cos 2x is 2 minus 2 sin 2x. So minus 2 3 into minus 2 sin 2x. Yes, minus 2 cos 2x. Okay. Now I can take out this minus e raised to the power x and 2 outside. So 2 by 40 is 20, and this will be 3 sin 2x plus cos 2x. Then the complete solution will be equal to c1 e raised to the power 2 x plus C2 e raised to the power 3x minus e raised to the power x by 20, 3 sine 2x plus cos 2x. Right? Now, case 5, right? So, when x is any other function of case 5, when x is any other function of x, right? So, then we say we have f of d as d minus m1 d minus m2 d minus mn. So we can resolve this into partial fraction. So 1 by f of d as a1 is a1 by d minus m1 plus a2 by d minus m2 plus an by d minus mn. Then particular integral will be equal to a1 d minus m1 a2 d minus m2 d an by d minus mn, and will be operated on the x, capital X, which is any function of x. Okay. Right. So a1 1 by d minus m1 x plus a2 1 by d minus m2 x plus an 1 by d minus mn x. Then particular integral will be equal to a1 e raised to the power m1 x integral x e raised to the power minus m1 x dx plus a2 e raised to the power m2 x integral let us rewrite this, which is equal to a1 e raised to the power m1 x e power minus m1 x dx plus a2 e raised to the power m2 x integral x e raised to the power m2 x dx and so on. Okay. An e raised to the power mn x integral x e raised to the power minus mn x dx. So this method is a general one and can therefore be employed to obtain a particular integral in any case and for any function of x. Next is to solve differential equation with variable coefficient. So a differential equation of the form a naught x raised to the power n dny by dxn plus k1 xn minus 1 dn minus 1 y by dxn minus 1 plus kn minus 1 dy by dx plus kn y is equal to some function of x. So it can be reduced into linear differential equations with constant coefficients by taking x as e raised to the power t, or t is equal to log x. Then let theta be is equal to d by dt. Then dy by dx will be equal to dy by dx will be equal to dy by dt times dt by dx, which is equal to 1 by x 1 by x dy by dt, because dt by dx is equal to 1 by x from t is equal to log x. Now x dy by dx is equal to theta y. So d square y by dx square is equal to d of dx, and then dy by dx is equal to 1 by x dy by dt. Now this is u into v form. Okay. So this is u into v. So v du, okay, minus 1 by x square dy by dt, and plus u dv, so 1 by x and dv. So dy by dt can d by dx of dy by dt can be written as d by dt dy by dt and dt by dx. You will understand this why we have written this way. Okay. So minus 1 by x square dy by dt plus 1 by x. So this can be written as d square y by dt square, d square y by dt square times dt by dx. Okay. And we know that dt by dx is 1 by x square, sorry 1 by x. Then this will become minus 1 by x square dy by dt plus 1 by x square and d square y by dt square. Right? Now 1 by x square, as taking 1 by x square as common, we have 1 by d square y by dt square minus dy by dt. So now this x square can be taken on the left hand side. So this will become x square d square y by dx square. So x square d square y by dx square is equal to theta times theta minus 1 times y, because this is theta square minus theta. Okay. And similarly, x cube d cube y by dx cube can be written as theta times theta minus 1, theta minus 2, and so on, right? Now substitute all these values in given differential equation. Then it will result in a linear equation with constant coefficients. Now which can be solved as before. Let us understand this with an example. Consider the differential equation x square d square y by dx square plus x dy by dx minus 4y is equal to 0. So this is nothing but x square d square plus x times d minus 4 y is equal to 0. So theta by theta into theta minus 1 plus theta minus 4. Okay, y is equal to 0. Again solving, theta square minus theta plus theta, then minus theta plus theta will get cancelled, then theta square minus 4 will remain. Okay, now we have to, now the auxiliary equation is theta square minus 4. Then solving, we will get theta as plus 2 and minus 2. Then complementary function is c1 e raised to the power minus 2t plus c2 e raised to the power 2t. Yes. Then solution is y is equal to c1 e raised to the power. So we know that we had taken x as e raised to the power t. Yes. So this is c1 x power minus 2 plus c2 x square, and this is nothing but c1 by x square plus c2 x square. So this is the required solution. Okay. Now we have another method to solve. Okay, before that, let me tell you when to apply linear approach and when to apply variable separable method. So if you find x dy by dx or y dx by dy in the differential equation, then apply linear approach. And if you find x dx by dy or y dx dy by dx, then apply variable separable method. Then apply variable separable approach. Okay. Yes, I was telling you we have another method of finding pi or method of variation of parameters. Method of variation of parameters. This method is quite general and applies to equation of the form y double dash plus p y dash plus q y is equal to x, where p, q and x, p, q and x are functions of x. Then it gives pi as minus y1 integral y2 x by w dx plus y2 integral y1 x by w dx, where y1 and y2 are the solutions of y double dash plus py dash plus qy is equal to 0 if its complementary function is given as y c1 y1 plus c2 y2 and w is called Wronskian of y1 y2 and w is given as determinant y1 y2 and y1 dash y2 dash, where y1 dash and y2 dash are the first derivative of y1 and y2 respectively. Okay, now we will not go into the proof. Let us understand this. Let us solve differential equation by this method. So d square y by dx square plus 4y is equal to tan 2x. So in symbolic form we can write this as d square plus 4y is equal to tan 2x. So complementary function is, to find complementary function we need to find auxiliary equation. So auxiliary equation is d square plus 4 is equal to 0, which gives d is equal to plus minus 2i. Thus complementary function is y is equal to c1 cos 2x plus c2 sin 2x. Now to find pi, y1 is equal to cos 2x and y2 is equal to sin 2x and x is equal to tan 2x. Now and w is equal to y1 y2. So let us directly put the values. So y1 is cos 2x, y2 is sin 2x and y1 dash is minus 2 sin 2x and y2 dash is 2 cos 2x. So 2 cos square 2x minus 2 sin square 2x, which is equal to 2. Thus pi is equal to minus y1 integral y2 x by w dx plus y2 integral y1 x by w dx. Then minus y1 is minus cos 2x integral sin 2x tan 2x by 2 dx plus sin 2x integral cos 2x tan 2x by 2 dx. Solving, we have minus half cos 2x and integral sin 2x tan 2x by 2 is equal to integral sec 2x minus cos 2x dx plus sin 2x integral sin 2x dx. Again simplifying, we will get minus 1 by 4 cos 2x log of sec 2x plus tan 2x minus sin 2x and minus 1 by 4 sin 2x cos 2x. Okay, minus 1 by 4 cos 2x log of sec 2x plus tan 2x then hence the complete solution is equal to complementary function plus particular integral, so which will be equal to y is equal to c1 cos 2x plus c2 sin 2x minus 1 by 4 cos 2x log of secant 2x plus tan 2x. So this is the required complete solution. Okay, so let's wind up here. We will solve few previous year problems in the next lecture. Okay, keep preparing. Thank you.